Exercise 35. This one's a little more complicated than most of the others. And it says, a rectangular circuit is moved at a constant velocity of 3 meters per second into, through, and then out of a uniform 1.25 Tesla magnetic field, as shown in the figure. The magnetic field region is considerably wider than 50 centimeters, which is the width of the apparatus. And so we know that it will enter, be fully consumed by, and then exit the magnetic field. Find the magnitude and direction of the current induced in the circuit as it is A, going into the magnetic field, B, totally within the magnetic field but still moving, and C, moving out of the magnetic field. Part D wants us to sketch a graph of the current in this circuit as a function of time, including the preceding three cases. And so, we have it drawn here. We have it to where it's a ½ meter wide and 0.75 meters tall, and it's a rectangle. The resistance is 12.5 ohms, and we can ignore the resistance and the rest of the wiring. And it's moving at 3 meters per second into the field. I've drawn it right up against the field because we're going to treat time at 0 as the point when it starts to enter the field to make the math more simple for us. And so, at time equals 0, there's no magnetic field affecting the apparatus at all. But after it's inside entirely, the magnetic field is affecting it at the total value of 1.25 Teslas. And during the transition, we have no real quantitative amount of the magnetic field. At least, we're going to have to measure it with calculus. And so, we use the equation where the EMF equals the negative of d flux dt. So that'd be negative dB dt times the area of our rectangular apparatus multiplied by the cosine of the angle between the magnetic field and the area vector of the apparatus, which are parallel. And so, like the other cases we've done today, we can ignore the cosine factor as it will just equal 1. And so we have it to where the EMF equals dB dt times by the area. I'm tempted to say that the area is changing as we go through, since the amount of area included within the magnetic field changes. But since the area of the apparatus itself doesn't in fact change at all, then we do indeed treat it as a constant. As soon as it's affected at all by the magnetic field, then the entire area of it is being affected as it establishes a circuit, a current throughout the circuit. So the area is constant, but the magnetic field we can treat as a variable because it's moving into the field. So as it starts to move in, it's experiencing just partial amounts of the field until it's fully immersed within it. And so in order to find dB dt, we just need to find the amount of change of the magnetic field according to time. So the change of the magnetic field is 1.25 Tesla since we go from 0 to the full amount of 1.25. So we just need to find the amount of time it takes to get from 0 to 1.25, which in the end is actually quite simple because the distance it must travel is just the width of the apparatus. Since it starts at the edge, it only needs to travel a ½ meter until it's fully immersed, and then it'll remain fully immersed until it starts to exit at the other end. So it's going at 3 meters per second. We have the velocity, we have the distance, so we just divide 0.5 by 3, and we have our amount of seconds, which ends up being which ends up being 0.166 continuous. And so our dB dt is simply equal to 1.25 divided by 0.166 continuous. And so plug that in, that equals 7.5. So our induced EMF is equal to 7.5 times our area, which gives for us negative, since we have to use the negative sign for this whole equation, that gives us negative 2.81 volts. And with it being negative, we can just take the sign out and then apply it to the direction of the induced current. And since the magnetic field is coming up out of the page, the direction following the right-hand rule is counterclockwise. And so that's the induced EMF. And we're looking for the induced current. And so we take that amount and divide it by the resistance. The resistance is pretty high, it's 12.5. Comparatively, that's high when you compare it to our voltage we have. And so the current ends up equaling 225 milliamps, or 0.225 amps. And it's going in the counterclockwise direction. And so that's the answer to part A. And conveniently, that's actually the only math we need to that we need in order to draw the rest of our conclusions. Because in part B, it asks us what the induced current is while the apparatus is entirely immersed in the magnetic field but still moving. And so initially we can think, oh, we should use the equation for motional electromotive force. But the equation for motional electromotive force is actually just another way to express Faraday's law. Under Faraday's law, we see that the magnetic field is not changing, the area is not changing, and the angle between the two is also not changing. And so because these are all constant, they're static, the EMF is 0, since we're measuring the change in flux and there is no change. And so long as it's entirely immersed in the magnetic field, there's no induced current in the apparatus. And then when it begins to enter, it undergoes the same change as it did when it entered, except in the opposite direction. And so as it exits, or rather, by the time it's finished exiting, it has an induced current of 225 milliamps, just as when it did when it entered, but in the opposite direction. So this time it's going clockwise. And that's the answer for part C. So for part D, it's asking us to graph the current as a function of time. And so I've shrunk the drawing so you can remember it up there. And I've graphed the current. So the current exists on the y-axis here and time on the x. And so we see that it decreases until it reaches its peak at our answer for A. And then increases till it hits the critical point at 0, which is our answer for B. And then it increases until it hits a critical point at C. Now this graph assumes that the field is actually exactly as wide as our apparatus. In reality, it would stop and flatline at 0 until it starts to exit, and then it would do the upward motion there. But assuming that the area is limited like that, it looks like a negative sign graph. The negative values are for counterclockwise currents, and positive values are for clockwise currents.